In this chapter, we'll start looking at the different effects that changing prices can have on demand. If we have n goods, so x1 through xn, then we can write the demand for each good as a function of the price of each good as well as income. These are exogenous parameters. So these are parameters that the individual cannot control. If any of them were to change for some reason, that could potentially alter not just the demand for that good, but the demand for every good. So if I change P1, that's not just going to affect the demand for good 1, it'll affect the demand for every good. Demand functions are homogeneous at degree 0. So if I multiply all the prices as well as income by the same factor t, the demand for each good won't change. This is because if I multiply all the numbers by the same factor, then the consumer's purchasing power hasn't changed at all, and the relative prices of the different goods has also not changed, so the same consumer can be expected to make the same decisions. If I have a Cobb-Douglas utility function, something like this, then the consumer is going to be spending a fixed proportion of their budget on each good. So they're going to be spending 30% of their budget on good X and 70% of their budget on good Y. If I have a CES utility function, something like this, then the share of income that the consumer will spend on each good depends on the price ratio. So you can see from these demand functions here that if the price of Y goes up and the price of X goes down, the consumer will be shifting more of their budget to X and less of it to Y. Now let's think about what happens if we were to change one of these exogenous parameters. So let's say we change the level of income. That would mean that the budget constraint would shift outwards, but the slope would stay the same. Now, it might be tempting to assume that as your income increases, you're just going to consume proportionally more of everything, but this doesn't really track well with how people actually behave, right? Because as your income increases, you won't necessarily just buy more of the same thing, but you're going to change your consumption mix. As your income increases, you're going to shift some of the spending away from things that you were forced to buy just because that's all you could afford, to buying more of the things that you couldn't afford before, but which you now can afford. So to put economic terminology on these things, normal goods are goods where the demand will increase as your income increases. So these are normal goods. Whereas inferior goods are ones where as your income increases, your demand for those goods will actually decrease. So for example, as your income rises, your consumption of canned tuna and ramen noodles is probably going to go down because you can afford to substitute better food instead of just eating more of the cheap stuff. This diagram shows an example of how the consumption bundle changes with income. As income increases, the budget line is going to shift out, but since the prices have not changed, the slope stays the same, and so the utility maximizing bundles on each indifference curve have the same marginal rates of substitution. Here, as income increases, the demand for both goods increases, so both goods are normal. In this diagram, we have the same shifts in income, but one of the goods is normal while the other good is inferior, because as the budget line shifts out, the quantity of Z decreases as the consumer is going to shift more of their spending towards Y. This example also shows that the definition of normal and inferior goods are relative, because in a two-good case, at least one of the goods has to be normal because we can't be buying less of both things if our income increases. Now let's think about what happens when, instead of changing income, we're going to change the price of one of the goods instead. As price increases, the quantity demanded will generally decrease. But there's two distinct effects that contribute to this. If we increase the price of one good while keeping the other prices fixed, then this good has become more expensive relative to everything else. So consumers are going to want to substitute away from this good and towards other things that are now relatively cheaper. This is called the substitution effect. At the same time, if price increases while income stays the same, then the consumer's purchasing power has decreased. And so even though in terms of income they have the same, their purchasing power has decreased, so they're now poorer in real terms. That means that they'll have to reduce their consumption somehow. This is called the income effect. This diagram shows the effect of a price decrease for good X, which we can decompose into the income and substitution effects. The initial bundle is going to be at X star, Y star, and a decrease in the price of X is going to flatten the slope. That's going to lead to a new bundle being chosen at X double star, Y double star. To separate out the two effects, let's imagine that after the price of X falls, to offset the increased purchasing power, that some money was taken away from the consumer so that they're going to be exactly as happy under the new prices as they were under the old prices. That is, we look at the original indifference curve and draw a tangent line with the new flatter slope, giving us the bundle at B. If only the relative prices had changed but real income had stayed the same, then the consumer would have substituted some X for Y, and so the increase from X star to XB captures the substitution effect. Generally speaking, however, when prices change, that's not accompanied by offsetting changes in income. And so if we reverse this and go from point B to X double star, Y double star, we can see that this increase in purchasing power is going to lead to an increased demand for both goods. This reflects the income effect. This diagram shows what happens when we increase the price of good X. Here, the initial bundle is on the higher indifference curve U2, and when the price of X increases, the slope of the budget line becomes steeper, giving us a new bundle on the indifference curve U1. Again, to separate the income and substitution effects, we have to imagine a transfer of income that will offset the effect of the price change on purchasing power. Since the price of X went up this time, the consumer is going to get something extra to bring them back to the original utility U2 at point B. Just as in the previous case, going from X star to the intermediate point XB gives us the substitution effect, while going from XB to the new value X double star gives the income effect. For normal goods, income and substitution effects move in the same direction. If the price of the good goes up, then it becomes more expensive relative to other goods so that consumers will substitute away from it. And at the same time, purchasing power goes down, and so consumers buy less overall. Both effects are going to reduce the quantity demand. Likewise, if the price of the good is going to go down, then both effects will increase the demand, which lead the consumer to buy more. However, for an inferior good, the income and substitution effects move in opposite directions. Higher prices still mean that consumers will substitute away, but for an inferior good, a reduction in purchasing power means that the consumer is forced to buy more of it. Likewise, if the price of an inferior good falls, then consumers have more purchasing power and thus purchase less of the inferior good. Again, this points in the opposite direction of the substitution effect. Typically, we assume that even if a good is inferior, the substitution effect will still be stronger, so that an increase in price will still lead to a reduction in demand overall. That means that a demand curve will be downward sloping. However, certain goods are so inferior that the income effect actually dominates, which means that when the price rises, the quantity demanded rises as well, which will lead to sort of an unnatural upward sloping demand curve. these are known as giffen goods. And one of the most famous examples of this is of potatoes during the Irish famine of the 1840s. As there was a blight that killed off most of the potato crop and caused prices to shoot up, the British government decided that no intervention was necessary because market forces would naturally lead the Irish to consume more of other foods instead because potatoes are now more expensive. However, since most of the population of Ireland ate potatoes pretty much exclusively and was too poor to afford anything else, as the price of potatoes went up, the demand for potatoes only increased, which made the famine even worse. We can plot the demand curve of x by holding the other arguments, py and I, fixed. And then we plot the price against the quantity demanded. Typically, it's going to be a downward sloping curve, but for a given good, we could have an upward sloping curve. Remember here that price is the independent variable, so what would normally be the x variable, but we plot it on the y-axis. Here we can see the process of drawing an individual's demand curve. We're going to fix income in the price of y, and for each value of px, we're going to draw a separate budget line on the top graph and find the utility maximizing bundle. Then, in the bottom graph, we're going to plot the x value from the top graph against the price px. In this example, we have the usual picture that as the price of x falls, the quantity demanded will increase, which gives us a downward sloping demand curve. As the demand curve plots x against px, if we change the price of the good, then we're going to be moving along the demand curve. If we change one of the other exogenous parameters, such as income, price of other goods, or parameters that influence the utility function, these are not going to be plotted on the graph, so changing one of the other exogenous variables will cause the entire curve to shift. For a Cobb-Douglas utility, like this one, we're going to have demand functions like this and this. So they're going to be proportional to income and inversely proportional to price. An increase in income is going to increase the quantity demanded at any price. This will cause the demand curve to shift to the right. We can see, though, that in both of these demand functions, the price of the other good doesn't appear. So if I were to change the price of y, that would only affect the demand for y, it wouldn't affect the demand for x. This is why the simplicity of the Cobb-Douglas utility function is both a strength and a weakness. It makes the problem a lot easier to solve, but it also gives us a very counterintuitive result that markets for goods operate entirely independently, but there's no interaction between them. A more realistic utility function would be a CES utility like this one, where we would have demand functions like this, and this. Here, the share of income that I spend on x is going to be dependent on the relative price of x to y. This means that there's going to be a stronger substitution effect. If x becomes cheaper relative to y, not only am I going to be buying more x just because it's cheaper now, but I'm actually going to be spending a higher percentage of my total income on it. So it's a stronger substitution effect than Cobb-Douglas. This means that the demand response will be stronger to a change in price, and so the demand curve will be flatter than under Cobb-Douglas. Here, if I increase income, that will once again shift the demand curve to the right because more income means a higher demand for x. But unlike with Cobb-Douglas, changing the price of y will also shift the demand for x. Because if y becomes more expensive, then x becomes relatively cheaper, so I'm going to substitute towards x, an increase in the price of y will also cause the demand for x to shift to the right. When we're plotting the individual demand curve, we hold the nominal income constant. But this means that as prices change, and as we move along the demand curve, the real purchasing power will also fluctuate. An alternative to the standard or Marshallian demand function is to hold utility rather than income constant. This is called the Hicksian or compensated demand function, as when prices rise, the consumer is compensated with additional income to keep them at the same level of utility. Therefore, the Hicksian demand curve is going to reflect only the substitution effect, as the income effect is exactly canceled out by this compensation. As we can see on this diagram, the Hicksian demand curve can be found by solving the expenditure minimization problem. If we fix the utility at a constant level U2, then as the price of X changes, we're going to draw the budget line tangent to the same indifference curve. This reflects how the nominal income is going to vary by just enough to keep the consumer at the same utility level. Plotting the price of X against the quantity demanded is going to give us the Hicksian demand curve, which here is downward sloping because a lower price of X means a flatter slope for the budget line, and with a convex indifference curve, that means that the tangency point is going to be further down on the indifference curve, giving us a higher quantity demanded. For the expenditure minimization problem, we're trying to minimize total spending subject to the utility constraint uxy equals u bar. That gives us the Lagrangian here. The expenditure function is going to be the minimized value of the objective function. So it's going to be the price times the compensated demand for X plus the price of Y times the compensated demand for Y. For any constrained optimization problem, we have the result that if we take the derivative of the value function, here that would be E, with respect to any variable, such as Px, that's going to be equal to taking the partial derivative of the Lagrangian with respect to that variable and evaluating it at the optimum. So here, that means that the derivative of the expenditure function with respect to Px is going to be the compensated demand function xc. This result is known as Shepard's lemma, which tells us if I take the partial derivative of the expenditure with respect to any price, that's going to give us the compensated demand for that good. Because the Hicksian demand function only reflects the substitution effect, for normal goods, it's going to be less responsive to changes in price than the uncompensated demand. Here, we can see that the uncompensated demand function is more responsive than the compensated demand. And because we're plotting the independent variable on the y-axis, that means that the uncompensated demand curve is going to be flatter than the compensated demand curve. If I have a Cobb-Douglas utility like this, then we're going to have demand functions. X is equal to I over 2px, and then y is I over 2py. If we then plug these demand functions into the utility, we're going to get the indirect utility function, which is I over 2 times the square root of px times py. By the duality principle, if we set the value function equal to u bar, then I is going to be equal to 2 times the square root of px times py times u bar, and this income level will be equal to the minimum expenditure necessary to reach U bar. So from the value function, we can get the expenditure function here. And then we can use Shepard's lemma to find the compensated demand functions. So if I take the partial derivative of this with respect to px, I'm going to get square root of py over px times U bar. This is the Hicksian demand for x. And if I take the partial derivative with respect to py, I can get the Hicksian demand for y. Now we can verify pretty easily that these are actually the same answers that we would get if we set up the expenditure minimization problem and solved it directly. If we want to gain some insight into the demand response to a price change, we're better off using an indirect approach. So by the duality principle, the compensated and uncompensated demands should coincide at the same value if I give the consumer just enough income to be able to reach the desired utility level U bar, which means that I plug in the expenditure function for I. So what this says is that the bundle that gets us to U bar with the least expenditure is also the same bundle as the one that we would choose to maximize utility if we were given the exact level of income necessary to get to utility level U bar. We can see in this equation that px is going to show up on the right-hand side both directly and indirectly through E. So if we take the total derivative of both sides with respect to px, we're going to get that del xc del px is equal to del x del px plus del x del e times del e del px. And if we rearrange this, we get that del x del px is equal to this minus this. If we now take a look at these two terms, we can write the first term as del x del px evaluated along the indifference curve, U equals U bar. And then for the second term, well, del x del e is really del x del I. And we can use Shepard's lemma, so del E del px is the compensated demand xc. So we can decompose the total impact on demand into these two terms. This first term represents the effect if we hold utility fixed at U bar. So this one is going to be the substitution effect. This second term is going to be the effect of px through the expenditure function on demand. This one is going to be the income effect. This is called the Slutsky equation. It's going to allow us to mathematically decompose the price effect on demand into the substitution and income effects. The first term of the Slutsky equation, this represents a substitution effect, and it's going to be negative as long as we have a diminishing marginal rate of substitution, because as we move along the same indifference curve and the slope gets flatter, the amount of x we demand is going to increase. The first term of the Slutsky equation, this represents the substitution effect. And the sign is going to be negative as long as I have a diminishing marginal rate of substitution or a convex indifference curve. This is because if I increase the price of x, that means I'm going to make the tangent line steeper. that's going to mean moving up the indifference curve, and therefore the demand for X is going to go down. The second term reflects the income effect, and for a normal good this will be positive. XC is also positive, so because of this minus sign, the entire term will be negative. So for a normal good, the income effect will go in the same direction as the substitution effect, but for an inferior good, this whole term will be positive because dx dy will be negative. If we go back to our previous Cobb-Douglas example, so with this utility function, then the uncompensated demand for x is this, for y is this. If I want to find the total effect of a price change, I take the partial derivative with respect to px. I'm going to get minus I over 2px squared. To do the Slutsky decomposition, we start with the compensated demand, which, if you recall from before, was this. Then if I take the partial derivative of this thing with respect to px, I'm going to get this guy. I can plug in the value function for u bar, which was this thing, and then multiplying through, I get that the substitution effect is minus I over 4px squared. So with Cobb-Douglas, exactly half of the total is the substitution effect. Now if I want to look at the income effect, the income effect is minus xc times del x del I. Well, xc, evaluated the optimum, is just going to be equal to x, which is I over 2px. And del x del I, that's pretty straightforward, is just 1 over 2px with a minus sign. This is going to be equal to minus I over 4px squared. So we can see that with Cobb-Douglas, the income and substitution effects have the same magnitude. They're both going to be exactly half of the total effect of changing the price of x on demand. With the demand function, x of px, py, and I, we can define elasticity of x with respect to each of its arguments. So we have the own price elasticity of x. That's going to be the percent change in x over the percent change in price, or del x del px times px over x. We have the income elasticity, which is the percent change in demand over the percent change in income. And we have the cross price elasticity, which is the percent change in x over the percent change in the price of y. Demand functions are usually downward sloping apart from given goods. So the own price elasticity is typically going to be negative. Now, sometimes the minus sign is omitted, so you'll see positive numbers for the own price elasticity, but what you should really think this means is that we're just omitting the minus sign or writing it as an absolute value. If the elasticity is less than minus 1, or equivalently, if the absolute value is greater than 1, then we say that the demand is elastic. So a 1% increase in price leads to a more than 1% reduction in demand. If the elasticity is greater than minus 1, or that means the absolute value is less than 1, then we say that demand is inelastic. A price change leads to a smaller demand response. if the elasticity is exactly equal to -1, then we say that demand is unit elastic. So the percent change in price is equal to the percent change in quantity in terms of magnitude. To see why this matters, we can see how the total spending, px times x, changes in response to a change in price. So that's going to be px times del x del px plus 1. And then if we multiply and divide the first term by x, we're going to get this. And this is just equal to the own price elasticity. If price goes up and demand goes down, and the good is inelastic, this whole expression is going to be positive, which means that total spending will go up. It's going to go in the same direction as the price change. But if the good is elastic, this whole expression will be negative, so total spending is going to go down, which means it's going to go in the same direction as the quantity. For example, let's say the price of cigarettes goes up. Cigarettes are an inelastic good. That means that consumers don't have much of a choice but to keep buying it. So while demand is going to fall, it's not going to fall by that much, which means that the total spending on cigarettes will go up. However, let's say that instead, only the price of one specific brand of cigarettes went up. The demand for that is usually going to be elastic, and so consumers are just going to switch to something else. So the price will go up, but the demand will fall by a lot, which means that the total spending will go down. We can similarly define price elasticities for the compensated demand function as well. So the compensated own price elasticity is going to be del xc del px times px over xc, and the compensated cross price elasticity will be this. We can write the Slutsky equation in terms of elasticities. So here we're going to have px over x times del x del px, and we're going to substitute here the Slutsky equation. So del xc del px minus x times del x del I. For the first term, we're going to note that at the optimum, x is going to equal xc. And then for the second term, we're going to multiply and divide by I. So we're going to have px times x over I times I over x del I. So what do we have here? Here, we have the compensated price elasticity minus the income elasticity times pxx over I. What's pxx over I? That's going to be the percentage of my income I spend on x, or the share of income on x as x. So this is the Slutsky equation written in terms of elasticities. Writing the Slutsky equation this way gives us a bit more intuition about the magnitude of the income effect, because it becomes a lot more significant depending on how much of our budget that good takes up. So, for example, we typically consider butter to be one of the main staple goods. But in practice, most people don't really care that much about the price of butter. Why? Because how much we spend on butter is going to be a small percentage of our total budget. So the share of income spent on butter will be low. That means that the income effect will be small. The effect of a change in the price of butter on our demand is not going to matter that much. We can now look at a few properties of elasticity. So as we showed before, demand functions are going to be homogeneous of degree 0. So by Euler's theorem, if I sum up the product of each of these arguments times the partial derivative, that's going to sum up to 0. So if I just divide each of these terms by x, that gives us the result that the sum of all three of these elasticities has to equal 0. We can also think about how elasticities aggregate across goods. So here's our budget constraint. If we take the derivatives of both sides with respect to income, well, on the left-hand side, we're just going to have 1. On the right-hand side, we're going to have this. And so if we multiply and divide the first term by x over I, so px times x over I times I over x del I. And the second term, we do the same thing. Then we get the equation that the share of income on x times the income elasticity of x plus sy times the income elasticity of y has to add up to 1. So what does this mean? This means that the weighted average, weighted by the share of income that you spend on the good, of the income elasticities has to equal 1. So a 1% increase in income means a 1% increase in total spending. That means that if your spending on X didn't go up by 1%, then your spending on Y must have gone up by more than 1%. If we instead take the derivative of the budget constraint with respect to the price of X, so on the left-hand side we have 0, on the right-hand side, we have 3 terms. We have just x here, plus px del x del px, plus py times del y del px. If we just multiply both sides by px over I, so on the right-hand side, we have this. The left-hand side just stays at 0. If we expand this out, the first term just becomes pxx over I. For the second term, we're going to multiply and divide by x. So we have pxx over I again, and then we're going to have px over x del px. For the third term, we're going to multiply and divide by y, so we'll have pyy over I, px over y del px. And just writing out what all of these are, this is the share of income on x plus the share of income on x times the own price elasticity plus the share of income on y times the elasticity of y with respect to px. If I move Sx to the left-hand side, what I get is that the share-weighted elasticity with respect to the price of x has to be negative. So, what does this mean? An increase in the price of x will generally lead to a reduction in the demand for x. It could lead to an increase in the demand for y as we substitute away from x and towards y. However, the magnitude of this cross-price effect is limited because an increase in the price of X means a reduction in our purchasing power, which means that overall we're going to be buying less stuff. So regardless of our propensity to substitute, an increase in the price of a good has to mean that we buy less stuff overall. We can't be substituting so much that we end up with more stuff overall, even though things are more expensive. If we have a Cobb-Douglas utility, then we have the demand functions. X is alpha I over px, y is beta I over py. An easy way to compute the elasticities is to take a logarithmic transformation. So I have log x is equal to log alpha plus log I minus log px. And from this form, I can very easily compute all of the elasticities because the own price elasticity is del log x, del log px, which is just minus 1. The income elasticity is del log x, del log I, which is just 1. And the cross price elasticity, well, in Cobb-Douglas, py doesn't show up in the demand for x, so that's equal to 0. We can also check all of the conditions that we found earlier. We know that the share of income on x is going to be equal to alpha. The share of income on y is beta. For homogeneity, if we sum up all of these elasticities, this is minus 1, this is 0, this is 1, so those will sum up to 0. For angle aggregation, this is alpha times 1 plus beta times 1. It's going to give me alpha plus beta, and we always assume that alpha plus beta is equal to 1. For Cournot aggregation, this is alpha times minus 1. This is 0, beta times 0. And that's going to equal minus alpha. Minus alpha is also equal to minus Sx. We can also use the Slutsky equation to find the compensated price elasticity. So by the Slutsky equation, this is equal to the own price elasticity plus the share of x times the income elasticity. This is going to be minus 1 plus alpha times 1 or minus beta. So because beta is less than 1, this lines up with our intuition that the Hicksian demand is less responsive to price than the Marshallian demand. The Marshallian demand had an elasticity of minus 1, while the Hicksian demand has an elasticity only of minus beta. If I have a CES utility with delta equals 1/2, so square root of x plus the square root of y, we have the demand functions like this. The math here is a lot more complicated than with Cobb-Douglas, but we can simplify it by looking at the share elasticity. So the share elasticity is how responsive the percent of my income that I spend on X is to the price of X. The share I spend on X is Px, X over I, where I can write that as log Sx is equal to log Px plus log X plus log I. So the share elasticity, or del log Sx, del log Px, is going to be equal to 1 plus del log x, del log px, or 1 plus the own price elasticity. The share of income spent on x is equal to 1 over 1 plus px over py. So if I compute the share elasticity, that's going to be px over the share. And then to find del sx del px, I'm going to use the quotient rule. So it's going to be minus 1 over py, because px doesn't show up in the numerator, times 1 plus px over py squared. Multiplying all this through, this is going to give you minus px over py over 1 plus px over py. If we have initial prices where px and py are the same, that's going to give me a share elasticity of minus 1 over 1 plus 1, or minus 1/2. And so the price elasticity is going to be the share elasticity minus 1, or minus 3/2. What that means is that a 1% increase in the price of x, if the price of x was initially equal to the price of y, means that I'm going to reduce the share of my income that I spend on x by 0.5%. And therefore, that means that the total amount of x that I buy will go down by 1.5%. If we have another CES utility with delta equals minus 1, then here, without going through and solving, the share of income I spend on x is given by this expression. If I compute the share elasticity, once again I have px over the share. I use the quotient rule here, so I have a minus sign, but then because x shows up in the denominator, I have another minus sign which cancels that out, over 2 times 1 plus this guy squared. Multiplying through, I get the share elasticity is the square root of py over px over 2 times 1 plus the square root of py over px. Another way we can write this is that this is just going to be equal to 1/2 times 1 minus the share. In general, if we have a CES utility function where the elasticity of substitution is sigma, which is equal to 1 over 1 minus delta, then the share of income spent on x will be 1 over 1 plus py over px to the 1 minus sigma. And if we compute the share elasticity, that's going to be 1 minus sigma times py over px to the 1 minus sigma over 1 plus py over px to the 1 minus sigma. Or we can write that just as 1 minus sigma times 1 minus the share. The demand elasticity is just going to be the share elasticity minus 1. And so from the Slutsky equation, we're going to have that the compensated price elasticity is going to be the uncompensated elasticity plus the share times the income elasticity, which is just 1, or minus 1 minus sx times sigma. We can now think about how changes in prices actually affect consumer welfare. So let's imagine that the price of x goes up from px0 to px1. Then To get to utility level U naught, at the old prices, the minimum amount we would have had to spend would have been given by this, whereas at the new prices, the minimum amount we need to reach the same utility level will be given by the expenditure evaluated at px1. The difference between these two expenditure functions is called the compensating variation. What this means is that if the price of x were to go up from px naught to px1, then in order for us to reach the same level of utility that we were able to reach before, we would need to be compensated by this much additional income to make up for the gap in expenditure. By Shepard's lemma, we have that the compensated demand function is the partial derivative of the expenditure function with respect to price, and we can get the compensating variation by integrating del E del Px dPx from the original price to the new price, and substituting here shows us that we can get CV just by integrating under the compensated demand curve. In this diagram, the initial bundle is x naught, y naught, and an increase in the price of x would bring us to x2, y2. But if we were to receive additional income to bring us back to the same indifference curve u naught, we would be at x1, y1. How much compensation this is can be calculated by integrating the compensated demand curve from px naught to px1. This gives us the compensating variation as the shaded area. Now suppose that the price of x increased to a level where the consumer isn't buying it at all, which is anything above the y-intercept of the demand function, or infinity if it doesn't have one. Then the compensating variation between the market price and this maximum price tells us the total value in dollar terms that the consumer gains from being able to buy the good. However, in reality, consumers are typically not compensated when prices change, so it might be more useful to integrate under the uncompensated demand function instead. In this diagram, we can find the compensating variation by integrating under the Hicksian demand curve from point A to point B. However, if the price increase is not offset by an increase in income, that's going to leave the consumer at a new lower utility level U1. We can devise an additional measure of the welfare loss by integrating under the Hicksian demand at the new utility U1 rather than the old one. This is called the equivalent variation, or EV, and asks, if we kept the old price, how much of an income loss would have an equivalent effect on utility as raising the price? This would be the shaded area found by integrating from point D to point C. A good middle ground is to integrate under the Marshallian demand curve instead, so going from point A to point C. This allows our utility to vary between U0 and U1 and gives us an area somewhere in between the compensating variation and the equivalent variation. If we have a Cobb-Douglas utility here, then from this one we know that the compensated demand for x is given by the square root of py over px times u bar. Let's start with an income of 8, py is equal to 4, and the initial price of x is equal to 1. With Cobb-Douglas, we're going to spend an equal amount on both x and y. That means we're going to buy 4 units of x, 1 unit of y, and our utility is going to be equal to 2. if the price of x were now to go up to 4, then our consumption of x, if the price of x were to go up to 4, then our consumption of x goes down to 1, y stays at 1, and our new utility is 1. To find the welfare loss, we can integrate the compensated demand function from the old price of 1 to the new price of 4. The primitive is going to be this thing, which, if you recall, was the value function, evaluated from 1 to 4. That's going to be 2 times 4 times u minus 2 times 2 times u, or 4u. What this means is that if we were to do this integral at the old utility level, this would give us a compensating variation of 4 times u naught, or 8. And if we were to compute this integral under the new utility, it would give us an equivalent variation of 4 times u1, or 4. That is, if the price of x goes up from 1 to 4, and we received an additional income of 8 to compensate for this price increase, so we now have 16, we would pick x equals 2 and y equals 2, which would get us back to the old utility of 2. Alternatively, if the price of x remained at 1 and someone took away $4 from us, we would set x equals 2 and y equals 1/2, which would bring us to the new utility of 1. So this reduction of income would be equivalent to a price increase, whereas a compensation of 8 would make up for the price increase. Alternatively, we can integrate under the uncompensated demand function. So if we integrate this from the old price of 1 to the new price of 4, this integrates to I over 2 log px evaluated from 1 to 4. So I is 8, so it's going to be 4 log 4 minus 4 log 1, or about 5.55. So this is going to be a measure of the welfare change that lies between the compensating variation and equivalent variation. So far, we've been using an approach that begins with an individual's preference relation, which is expressed by a utility function, and then we optimize this to find the best choice that the consumer can make. However, we can alternatively take the opposite approach. Starting from looking at the pattern of choices that we see somebody make, and then use that to infer what their preferences must be. This is called the theory of revealed preference. To derive the revealed preference relation, we're going to say that A is revealed preferred to B if A and B were both available for this person to choose, and we observe them choosing A. Then, in any other situation in which both A and B are valid choices, the same person may not necessarily choose A, but they would never choose B. If you choose A over B in one situation, you have to consistently choose A over B when both are available. In this diagram, suppose that along budget line I1 we choose A. That means A is revealed preferred to B because both A and B were available, but I chose A. Then B would be a valid choice at I2 because with that budget line, I can't afford A. A is not an option anymore, so it's valid for me to choose B. But at budget line I3, this budget set includes both A and B. So anything that the same person chooses needs to be at least as good as A and thus be better than B. So on budget line I3, we can't choose B. Let's say we have two bundles, C and D, that are revealed indifferent to each other. What that means is that whenever C and D are both available, either both C and D are valid choices or neither of them is. So either I'm indifferent between C and D, or I can find something that's better than both of them. If I have prices PXC and PYC that form a budget set where I choose C, then under these prices, D must cost at least as much as C does. Because if it costs less, then I could buy something that was strictly better than D and therefore strictly better than C. So I would never choose C if I could get D cheaper than C. Likewise, if I have prices PXD and PYD where I choose D, then under these prices, C must cost at least as much as D. If we rearrange these two conditions, I have that under the prices where I would choose C, I have that this is less than or equal to 0, and under the prices where I would choose D, I have that this is less than or equal to 0. So if I were to simply add these together, I get that PXC minus PXD times XC minus XD plus PYC minus PYD times YC minus YD. This whole thing is less than or equal to 0. This expression looks a little complicated, but it's best written in vector notation as delta P dot delta X is less than or equal to 0. So that prices and quantities tend to move in opposite directions. I'm going to substitute away from the goods that are getting more expensive and towards the ones that are getting cheaper. Now that we have an idea about substitution generally, we're going to investigate the relationships between goods more closely and what makes them substitutes or complements.